the bus doesn't leave till 10, so I figured, what else am I going to do? Stand around until 10 o'clock?
You could have gone some more sleep.
All right, so I wanted to go back and correct my mistake that I omitted. I forgot to include a portion of the solution. Yeah, you were right, Samson. So we had gotten to the transform of our solution was 2 over s minus, and we fix this up, s plus 1 plus 2 over s plus 1 squared plus 9 plus the sum, because we had a geometric series in there, negative 1 to the n, 4 over s. You can go ahead. And then all of this is times e to the minus n pi s. And we're summing, we're going to just do that. All right, so I had included a cosine 3t term for this s plus 1 over s plus 1 squared plus 9, but I'd forgotten to include the sine for the 2 over s plus 1 squared plus 9. And the same thing here. I'd included the cosine, but not the sine that comes with this 1. So I wanted to write the full solution after we apply the inverse transform. So we get 2 times, factoring out the 2, 1 minus, so the shift, we have an exponential function, e to the minus t, times cosine 3t from this part, plus 2/3, because for the sine we would need a 3 in the numerator, and I don't have the 3 in the numerator there, sine of 3t, plus I'm going to factor out this 4, and then we have the sum of 1 minus, and then this gives us a t shift, e to the minus t minus n pi cosine of 3t minus n pi. And I'm going to continue down here, plus 1/3, because I don't have a 3 here, sine of 3t minus n pi, and then this is all times our unit step function, t minus n pi. Yes. Oh, yeah, I forgot that term. Thank you. There we go. Yes.
Let's start from the left. Didn't we already factor out the 2 in the front, so shouldn't it be 1/3?
Oh, yes, you were right. There we go. Now we finally have the correct solution. All right. Thank you, Samson, for catching that for me.
Thank you for the shout out in the video, Mr. D.
I had, so interesting, in my notes I had it written down.
Oh, okay.
I just didn't write it.
Oh, okay.
When I look back, I was like, wait a minute, why did I not write that on the notes? So anyway, there we go, the full solution. And I put a correction at the end of the video. And interestingly, the correction has sound. The rest of the video does not.
So it's just like a jump scare?
Yeah.
Your volume's all the way up.
Right. It comes across. Okay, I'm going to correct the mistake that I made. But really loud. All right, so now we're going to jump to the Dirac delta function. I'm just going to draw a line here. Now we're on to our actual lesson. So at the beginning of the chapter, when we defined the properties of the Laplace transform, we saw that f of s equals 1. This cannot be the transform of a piecewise continuous piecewise continuous function on 0 to infinity of exponential order. We saw that for piecewise continuous functions of exponential order, the Laplace transform of that function approaches 0 as s approaches infinity. So this doesn't hold for that. So it's not the Laplace transform of a piecewise continuous exponential order function. But we said it's possible that did not mean that this was not the Laplace transform of some function. Some function. So today we're going to see what that function is. So today, look at what we call a generalized function with a Laplace transform of 1. So this is not a function in the normal way we think of a function, but we call it generalized function. So to get to start, we talked about a unit step function. Now we're going to talk about a unit impulse function. And that will get us to the Dirac delta function. So our unit impulse function is delta sub a of t minus t0 equals 0 for 0 less than or equal to t less than t0 minus a. It's 1 over 2a between t0 minus a and t0 plus a, and then to 0 again. And a is greater than 0, and t0 greater than 0. So the way we think of this function, we think of a being very small. So the function is a very large function with a very large magnitude, that acts for a very short amount of time. So an example, some of the physical examples that we typically talk about is like someone, like the driver, someone hitting a golf ball. Very large force acts for a very small amount of time. Or the baseball bat hitting the baseball. A large force acts for a relatively small amount of time. Hitting something with a hammer. Very large force for a very small amount of time. And now we're going to look at the limit as a approaches 0. That gives us our Dirac delta function. Being very imaginative with the name, delta, because this is delta. So the Dirac delta function is delta of t minus t0, and that is the limit as a approaches 0 of delta sub a of t minus t0. Now, delta, the Dirac delta function is not a true function, because but we can define it by its properties. So the properties of the Dirac delta function, we could write delta of t minus t0 is infinity for t equals t0 and 0 for t not equal to t0. So not one reason it's not a true function is I'm saying this function equals infinity. So that's a very big gray area in actual technical formal mathematics. We don't say things are equal to infinity. They can approach infinity, but this is the property of one of the properties of the Dirac delta function. It's infinite for basically for 0 time. And the integral from 0 to infinity of delta of t minus t0 dt equals 1. So again, mathematically that doesn't really make sense, because delta t is 0. We have infinity times 0. We're saying, oh, infinity, in this case, infinity times 0 is 1.
What is this? That makes sense to me.
So,
It doesn't matter.
yeah, so the Dirac delta function is, imagine a golf club hitting a golf ball, but the golf player that hits the golf ball is really, really good and really, really strong, so hits the golf ball with an infinite force for 0 time.
Superman. Oh, it's like Superman punching football. You
Right,
just have
right.
to swing hard enough.
Right.
And then you'll get there. How did someone figure this out?
So,
They just made all
Paul,
this
yeah,
stuff.
so Paul Adrian Michael Dirac, it's named after Dirac, worked on the foundations of quantum mechanics, and he came up with this idea because it was useful in certain applications. This thing that's infinite for a very short amount of time. He shared the Nobel Prize in 1933 with Schrödinger for work on quantum mechanics. And so they both won the Nobel Prize. So what we want to do is look at the Laplace transform of the Dirac delta function, because we can imagine describing some physical system. We'll do a problem in a second, where we have a very large force that acts on the system for a very short amount of time. So if we'll do a spring mass system, and we're imagining that the mass is just sitting there on the spring, and then suddenly maybe we have a little super strong pneumatic piston that just suddenly hits the weight and starts the thing moving. So we're going to say for t greater than t0, the Laplace transform of the Dirac delta function, delta of t minus t0, is e to minus s t0. Why? We're going to write the Dirac delta function, or not the, sorry, we're going to write the unit step function in terms, the unit impulse function in terms of the unit step function. We're going to write the unit impulse function in terms of the unit step function. So we can write this as 1 over 2a times, oops, don't need that, 1 over 2a times the unit step function t minus t0 minus the unit step function of t minus, sorry, I wrote this wrong, t0 minus a, and this should be t0 plus a. So in terms of the unit step function, the unit impulse function can be written like this. And then we're going to do the Laplace transform of this function and take the limit as a approaches 0. So that's going to be 1 over 2a times, well, the Laplace transform, we know the Laplace transform of these. This is e to the minus s t0 minus a over s minus e to the minus s t0 plus a over s. And I'm going to simplify this. I'm going to factor out an e to the minus s t0. So we get e to the minus s t0, e to the sa minus e to the minus sa over 2as. And this should not be minus. So as a approaches 0, if we take the limit as a approaches 0, this gives us an indeterminate form. We approach 0 over 0. So we apply L'Hopital's rule. Is that the first time that's shown up in this class? We might have done one other problem that we needed L'Hopital's rule for. To find the limit. So we're saying the Laplace transform of the Dirac delta function equals the limit as a approaches 0 of the Laplace transform of the unit impulse function. And we've just found this part. So that's going to be e to the minus s t0, limit as a approaches 0. I'm going to apply L'Hopital's rule to this right away. We know this is an indeterminate form. So we get s e to the as plus s e to the minus as over 2s. Is this right?
Then you cancel an s, it goes to 0. Then you get 2 over 2, you get 1.
And then you're right. As a approaches 0, we get this limit is 1, and we get e to the minus s t0. Yes. Take the derivative with respect to a. And we get our result. And we can see now when t0 equals 0, the Laplace transform of the delta function of t equals 1. the Dirac delta function, when t0 equals 0, has a Laplace transform of 1. And again, different kind of function because our Laplace transform does not approach 0 as s approaches infinity. And we have those other strange properties with the integral in our properties of the delta function. And we'll kind of, after we do an example, we'll kind of talk about how mathematicians fixed all of that up, or put it in a context that was palatable to mathematicians. I'll put it that way. Physicists tend not to worry about that stuff. It's like, oh, it works, it makes sense. We're not going to worry about it. Let the mathematicians deal with that. So we'll talk a little bit about how the mathematicians dealt with it. So the main thing that we wanted to know was that the Laplace transform of the Dirac delta function is e to the minus s times t0. So you can imagine when this shows up in an equation, differential equation, for example, that we end up with solutions that involve the unit step function because we get this e to the minus s term in our transform. Okay. So we want to solve y double prime plus 16y equals delta t minus 2 pi. And y of 0 equals 0. And y prime of 0 equals 0. So we can imagine this. This is a spring mass system. With no damping. So this is a spring mass system that is at rest with 0 displacement, 0 initial velocity, that at time equals 2 pi gets driven with a very large magnitude force. So we're going to take the Laplace transform of our system just like we've done. So we get s squared y of s minus s y of 0 minus y prime of 0, writing all the y terms just to be, just so I have them all there. We'll do our substitutions in a second here. Plus 16y of s equals e to the minus 2 pi s. So we get s squared plus 16 y of s equals e to the minus 2 pi s. So y of s equals e to the minus 2 pi s over s squared plus 16. And I'm going to fix this up a little bit. This is 1/4 of 4 e to the minus 2 pi s over s squared plus 16. So this we have a 4 over s squared plus 16. That gives us a sine. And we have an e to the minus 2 pi s. So that gives us our unit step function. So we get 1/4 sine of 4 times t minus 2 pi times the unit step function of t minus 2 pi. And the sine of 4 times t minus 2 pi is the same as the sine of 4t. And so what we have here, if we graph this solution, better horizontal line there. So our solution, we have nothing. Until t equals 2 pi, because our unit step function is 0 until t equals 2 pi. And then we have a sine graph. So we have no motion until t equals 2 pi, and then we have a sine wave. So we hit it very suddenly for a very short amount of time. Right at 2 pi, then it starts moving. Now we can imagine it gets more complicated if it has some initial displacement or some initial velocity, and then we use then we get some kind of impulse, and then some things happen. It gets more interesting when we get sums of Dirac delta functions that apply at different times.
Are we going to do that?
I think there are a couple of problems where there's some sums and it just gets a little more complicated, a few more terms in your solution. But in general, when you're using the Dirac delta function, really what it does is introduce this factor of e to the minus something s, so you get a unit step function somewhere. Yeah. So again, the Dirac delta function doesn't behave like a normal function. Doesn't make mathematical sense to say it's infinite at a point. Initially, mathematicians didn't really accept it, even though it was useful. But then in the 40s, a mathematician by the name of Laurent Schwartz studied it in a rigorous way and defined it mathematically as, we're going to say, the Dirac delta function of t minus t0 is the integral from 0 to infinity. This is not an equals here. This is our mathematical definition of the Dirac delta function. F of t delta t minus t0 dt equals f of t0. So we can take this as our definition of the Dirac delta function. The function such that this integral equals f of t0, which gives the integral from 0 to infinity of the Dirac delta function t minus t0 dt equals 1 if f of t equals 1, as we expect. And the integral from 0 to infinity of e to the minus st times delta t minus t0 dt is e to the minus s t0. So defining it in this way, the mathematical properties, it makes more sense mathematically, but everything else that we want the Dirac delta function to behave like, the Laplace transform, the integral to be 1, comes out from this definition, and we don't have to say with this definition that the function equals infinity for a 0 amount of time. So that made it palatable, more palatable to mathematicians if we define it this way. So you might argue it's semantics. Well, it behaves exactly the way we describe it the other way, which is kind of what the way that Dirac did things. Well, we can define it this way, but it behaves just like I said it does. So why not just say it's this other thing? So, there we go. I've made some edits to the homework on Schoology and added some notations because there's a couple of problems where there's some errors in the book, the way they state the problem. There's some problems with errors on, was it 7.4 part 3 where they said solve equation 15, but we needed to actually solve equation 11. So look on the Schoology. I just found I was very good at finding all the errors. I spent